Hey everyone, we're going to finish off chapter 9. This is 9.3, measures of regression. So once we have our regression line, we're going to be looking at variation about that line. So there's a lot of technical details here at the beginning that as you get into the problems you won't really have to worry about, but it's the background of why we are doing it. But really that picture tells the story. I know there's a lot of variables, but we're really just looking at, in general, variation of our predicted dots. So if we do some highlighting here, right, here's a actual dot from the like say the study, right? The regression line is the model that we've come up with, and then we're looking at variation. How far are these dots on average from that line? Basically what we're really after is how good is our prediction model. Is it really good? Is it pretty good? What kind of variation do we really have? The nice thing is when it all boils down after you get through a lot of this technical details, and you can look at that if you would like and get more into it, but we're really looking at what's called this coefficient of determination, and the notation for it is r squared. And it's the ratio of explained variation to total variation. But the nice thing is the easy way to calculate it is it's just r squared, and we already know how to calculate r. So r squared is just one further step, just square the correlation coefficient. So the wording starts getting confusing, right? Or from 9.1 we had the correlation coefficient. If we write it as r squared, it becomes the coefficient of determination. For example, here, say r is 0.9, then r squared, you just square 0.9 and you get 0.81. We're not really too worried about the nuts and bolts of the calculation of that r squared. We really are focused on the interpretation of it. And so that next statement is the key to that. So this means that 81% of the variation in y can be explained by x, meaning that x is doing a pretty good job of explaining y, right? There is a 19% of the variation that's, I'm just highlighting everything, that is unexplained due to other factors. But it looks like x is the major piece of the explanation. Okay, so let's put this all in an example, and that would help. So let's suppose we have a study, and we have a relationship between the size and weight, maybe length and weight of brown bears. 8 brown bears were captured, tagged, who wants to do that, and recorded and then released. Below is the data collected from each bear in the sample. So let's run through finding all of these values and then making the final interpretation. So let's load this into StatCrunch. So as far as calculations go, you're really just focused on StatCrunch on that. So we'll load the data, and this data set is in the groups folder. So let me access that. It's on the last page, and that's bear length versus weight. Okay, so I've got the data loaded. And then I'm going to that same location we go through of all of chapter 9, stat, regression, simple linear. We're going to put the x and the y in the correct spots, and then we're going to click compute. Okay, notice you get both. You get the r correlation coefficient 0.897, but you also get the r squared. It calculates it for you. You don't even have to square the number, 0.805. Okay, so we got that. We'll jot that down on our handout. So we came up with, what was that correlation coefficient? I'm pretty sure it was 0.897. This is the downfall of doing this on an iPad. You can only look at one screen. And then the r squared was 805. Okay. So what do those numbers tell you? We already know what the correlation coefficient tells us, that part A, right? That's showing a strong, positive, linear correlation. What does r squared tell us? And I can do that by this fill in the blanks statement. So about 80 point, if I convert that to a percentage, 80.5% of the variation in the variation is in the y. So the y comes first in the sentence. So the y variable is the weight. Can be explained by variation in the x variable, which is the length. And then the other, we want these to add up to 100%, right? So 100% minus 80.5 is 19.5%, right? So this value is, formula-wise, 1 minus r squared, which is 1 minus 80.5, or I guess in this example, 0.0805, which is 0.195. Same as 19.5%. Okay. And that's it. That's all we're doing. That's not too bad. Let's try another piece, and then there's only one more piece. Right? The last thing is this, what's called standard error of estimate, S sub e. It's the standard deviation of the observed y values about the predicted y value. So when you're looking at these variables, you'll see these subscript i's. That's the observed values, the value that you get actually from the data and the sample. The y with a hat on it, that's the value you get if you use the equation to make a prediction. Okay, so there's a formula for it. There it is. And this is giving, remember, standard deviation measures spread. So this is telling you how spread out the values are. Right? So the closer the observed y values are to the predicted, the smaller that standard error of the estimate will be, that standard deviation. And I gave you the sentence for the interpretation. The standard error of the estimate of the y value for a specific x value is about S sub e. Okay, so let's practice finding the S sub e and then making the interpretation. So for the previous bear example, the nice thing is we don't have to use that formula. We have the technology. It's all given on this output. If you look on that under simple linear regression, what is it? The very last line, about 8 lines down, estimate of error standard deviation. That's the S sub e. It's right under the r squared. So 66.6. I'm going to write that down. 66.6. This says round to 2 decimal places. Okay, so I guess 66.60. And the unit of measurement always matches the y value. So this is weight, which is pounds. Okay. And then the interpretation. The standard error of estimate of a bear weight for a specific bear length is about 66.60 pounds. So we're talking about it for a specific length. If we already know the length of the bear, then how spread out are the weights for that length, right? And we have a measurement for that. On average, we're about 60 pounds from the mean. Let's put it all together and do one example that has everything that we've done in this section, and maybe a little more. All right. So we have a new study. This table shows the ages and salaries for a random sample of engineers of a company. All right. And first thing we'll need to do is put it into StackWrench, get all the numbers, and then we'll fill in the blanks with the interpretation, and we're good. Okay, so load it up. We're going to get rid of bear weights and links, and we're going to average salary for engineers. There it is. Stat. Regression. Simple linear. The X is the age. The Y is the salary. Compute. And we get our output. All right. So we've got the R squared, the 0.851. We've got the S sub E, 5.09. And those are the two values that this problem is asking about. So we'll jot those down in our handout. Okay. So R squared, 0.851. And then the SE was 5.09. Okay, that's what I got from StatCrunch. Now let's finish it off with the interpretations. So the interpretation of R squared is about, convert that to a percent, 85.1% of the variation in the Y variable, salary, can be explained by the variation in age. And then about what we want these add up to 100, so 14.9% of the variation is unexplained or due to chance or other variables. The error of estimate is 5.09. Remember, that's a Y value, so that's salary. And that salary is in thousands of dollars, so that's something to note there. So that'll help in our interpretation. The standard error of estimate of Y variable, salary, for a specific X variable, age, is about $5.09. No, not just dollars. $1,000. Right? $5.09,000. Or a better way to write that is just 5,090. Right? Move that decimal over 3 places. Okay. So for a specific age, we'll see a variation in the salary by about 5,000, right? Average deviation from the mean. Okay, that's really it from 9.3. So just a little extra piece about variation. So not too much more. So now we've got chapter 9 done. We've got correlation coefficient, linear regression, line of best fit, and then these new concepts about the variation. So give 9.3 a try, and let me know how it goes. If you have any questions, send them my way. Okay, hope all is well. Thanks. Bye.